the most important part on how to add a new module is the following. We have two ways, basically. You can add it to BESMod itself, which would make us happy, or you can create your own package and keep it for yourself. I mean, if you like BESMod, if you like Xlib, if you like open source, then you should always use the first option. And yeah, if you kind of have maybe industry projects or are too lazy to contribute to open source software, then that's definitely a bummer. If you create your own package, there are examples. So for example, for a contribution of mine, I added a separate package, but which is also available open source, which is really specific for one aspect. So all these models, studies, values, and so forth are in this repository. But you can basically, as I've shown today, just say, okay, file, new package, and then start to work. If you choose to add it to BESMod, you just go to the issue section and add a new issue, describe what your new module does. You can assign yourself, and then a branch is created for you where you can work on. Afterwards, you can open a pull request. You will get feedback on how you modeled. So even if you don't know Modelica at all, if you don't know Git, this does not mean that you can't start. You always have to start somewhere. And if you do a pull request, I'm happy to give review and show maybe tips on modeling. And you also contribute to open source software. So this is pretty cool. And yeah, so these are the concepts on how to hopefully add to BESMod, because as more modules we have, yeah, the better BESMod gets, basically. And now one example on how to do this. If we look at the example we worked on today, we have basically, in the case for the boiler, a lot of electricity we generate, and currently we don't get a lot of money for this. So one idea could be to increase the self-consumption of photovoltaic. And the idea is to just use direct electric heating using infrared to increase the room temperature as soon as we have PV overcharge. And to do this, we basically have to adjust or create a transfer model. We have to create a control model because we have to control this. And maybe we also have to adjust distribution if we need measurements on how much electricity is generated. And afterwards, if we implement this, we can also enable debugging. So if we implement new systems, we can always test and disable single subsystems, as I've shown by not simulating ventilation. What you can also do is we have separate test packages. So for each module you create, you can make a dedicated test and check if your module works. And if it works in there, it typically works in the simulation of the energy system as well. So how to implement new modules. If you want to change now this transfer model, the best way is to open the one which is selected, go into the base classes package, because in here we have the partial transfer model. This one we have to extend because we want to extend the container basically of the module and say direct electric heating. And we want for now to put it into the example tutorial package. And yeah, basically what we have, we want to simulate a direct electric heater. I would make this a little bit quicker. So we can just add a prescribed heat flow rate. Just assume a heating efficiency of 100%. And then a fixed heat flow rate, because on infrared heating, I would assume that we don't have any convective heat transfer. So we can just say this is 0. Then we get the first issue. We have to remember everything is vector sized. So these ports are vector sized, because we can have multiple zones, multiple thermal zones. So the best option is to also make this model for direct electric heating vector sized. In our example now, this is 1, but if we select the high order model, we directly have the model in a way that it works with the high order model as well. We connect the heaters. This one we don't have to change. Here we have to say, okay, this one is 0 for all arrays. So select each, and final for good modeling as well. And now we say, okay, we want to, the input of the heater is typically a value between 0 and 1. So we will add a gain block, which is also vector sized. And this gain block receives the signal from the, wait, I will put it in here, from the transfer control bus. So from the control domain, say, okay, we now have to name the variable. We will call it U, so input for direct electric heating. And the gain factor itself, well, first assumption would be to size the direct electric heater in a way that it matches the heat flow rate, which is required. And this system has as a top-down parameter the Q heat flow rate of the building. So we can say, okay, the gain value is just Q flow nominal. So if we say the heater should operate fully, we will basically have automatically the correct value if we change the heat flow rate of the system. So this is nearly finished. We have already the interaction with the thermal domain. What is missing is this electrical port up here. Because if we use electricity to do direct electric heating, we have to specify how much electricity we are using. And you can find under utilities, electrical, you have different options. You can say, my system does not use electricity at all, and put in a zero load model and just like connect it like this. Yeah, but we use electricity in this part. So we can say wheel to electric connector, so a conversion. And this conversion block specifies if the system is used only for the load, so energy consumed, or also if we generate electricity. So if we now, for example, add a CHP model in the hydraulic system, which generates electricity, we could say, okay, this both consumes and generates electricity, but now we just use it. So we just going to disable generation. And as we have an array, we will quickly add a multi-sum as an input to summarize all the gain output. And if I did not make any error, this model should work. And to check if it not only checks, but also simulates, you can go again into the transfer system of the electric domain, go under tests, and duplicate the existing tests. Also put it in your own model and say direct electric heating test. And this little test, you can say, okay, I want to change my transfer system to the one I just implemented. I don't have any further parameters which I have to change. And then you can quickly check if it works. And you will see that it does not work because we have a missing input connector, because we require this system to be controlled. And so now we can add this by creating a connector and putting in some source. So maybe I will just say sine wave. I don't know, just keep it constant, wait. Just a constant heat flow rate, which has array size 1 for now, because our system also has only one dimension. And specify we connect everything to everything and select the variable we just designed. Say, okay, this is 0, and then see if our example works. And by implementing this, you kind of know, okay, I have to specify this value in the control block to be able to use this model. And as this now works, we know, okay, the module itself works, and we have a higher confidence that it will work on the system level as well. After now changing the transfer model, we have to change the control model. So we go under Systems, Electrical Control, Base Classes, and change the base class and extend from this and say, okay, this is self-consumption increase control or something. Some fancy name. Again, edit or put it into our own model. And what we now do, again, in here we have the same top-down parameters, so the number of zones and the number of heat flow rate. What we can now do is we can say, okay, we have a PI controller, and the PI controller should act on the room temperature. So the measurement of the PI controller, we can access the room temperature from the building measurement bus. And here again, we see we need an array, and the PI controller is not an array. So we again have to specify that this is an array as well. Now it works. So we can use the T-zone measurement value, and we can use the T-zone set temperature from the user profiles. So if I now, for example, simulate a night setback in the user profiles, it will automatically update the zone temperature, and all the control models directly receive the updated value. And lastly, we say we only want to use the direct electric heater if we have surplus electricity which is generated. So we're going to logical. We're using some hysteresis to say, okay, as soon as the generation of electricity, which is already available as a measurement, as soon as this electricity which is generated is maybe higher than 100 watts, we turn on the direct electric heating, and if it is, let's say, below 10 watts, we are just going to turn it off. Just a basic hysteresis to prevent frequent switching. Then we say, okay, we are going to only use this output if this is true. This is an array output, so I'm going to make the switch an array as well. If we don't use the PI controller, I'm going to add a constant 0 block, which again is also an array, which is 0, final, and each. Connect this one. Now we have the issue that we have basically a hysteresis, which is scalar. So the generation heat pump of electricity is always scalar. So I'm just for now going to give them the 1. We have to make a for loop in the code section, and the output will be connected to the variable which will be suggested because we have added it into the transfer system. Last but not least, we have to parameterize the PI controller. We say, okay, we use a PI controller with a gain of, let's say, 0.01 and a time constant of 300 seconds, typical values which most of the time work. Maximum output is 1, minimum is 0, and the rest just stays the same, stays default. And last, we have to go into the text section because we have a array and we say, okay, for I in 1 up to n parallel demand, we're going to loop and connect the hysteresis to all the switches using I. So this is, for some of you, maybe advanced Modelica, or some of you not. But sometimes if we develop new models, we have to go into the text section. And now there are some warnings about missing eaches and so forth. So this would not work in OpenModelica. For now, it works in Dymola. So obviously, we should keep on improving the model until we get no warnings. But for now, it's, I guess, all fine. And now we can select these newly created modules, go to electrical, transfer. We see, we have the direct electric heating system. We have no further parameters. And we have the control system where we can select the self-consumption increase control. We did not propagate any parameters, so we could have propagated the PI values and changed them. But for now, keep it simple and click on save. And maybe for the C pump value, we're going to simulate it. And I'm now going to simulate, there was some over generation, I guess. Or maybe let's simulate it with the gas system, because this was our first assumption, to increase the self-consumption with the gas boiler. So here we have 80% still of the roof area is PV simulated, and then we can see if this changes or if it works as supposed. And now we have already different domains. So we have heating using radiators, and we have heating using this direct electric heating. And we see, okay, we get an error. This is most likely because of the control model. So we see, okay, the control hysteresis is 1 at time something and then 0 directly again. So this is now going into debugging of Dymola. If we develop new models, this is like BESMod is not magical. So if you develop new models, you still need to be an expert on Modelica. What happens in here, I guess, is that we've already had this error once. As soon as the hysteresis goes on, the direct electric heater turns on as well, and then uses directly electricity to heat. But then the electricity generation turns to 0 directly because we use electricity. And then this results in switching behavior of this hysteresis control. So what we can do is, for example, increase the limit on when to kind of use this hysteresis. So for example, go to maybe 3000 watts overcharge. We could also add PT1 elements to kind of decouple this behavior a little bit. So there are a lot of options. Maybe I will now go for this decoupling of dynamics at a first order model to the measurement. Normally measurements always have some like sensors always have some kind of inertia, so it's nothing really unphysical to do here. And I will add some kind of time constant of 60 seconds. And this should hopefully improve the simulation or make it run. Yeah. But I mean, if you add new modules, you will encounter such issues. But I guess the 6 of you are still in here already. Maybe know some Modelica and know how to fix results. And now we see, okay, perfect. We have. Oh wait, I have to delete this plot. So we have a lot of switching behavior. You can really neatly see here that as soon as we generate electricity, we have this small time constant and directly use it for heating of the room. So this is definitely not a good system to implement in reality. You would definitely, or you are definitely able to improve this control behavior. But I mean, I just implemented it in 10 minutes. So not to be expected to be good anyway. And we can also see, okay, how does this affect our results? I did not finish the tutorial as planned because we ran out of time. So I will quickly update the last part, just so you don't be concerned about the difference maybe in the result view or some other view like date and so forth of my Windows PC. I quickly wanted to show you how you can now compare the results of direct electric heating to the ones without direct electric heating. We actually did not simulate in the tutorial the building energy system with the gas boiler correctly sized without direct electric heating. So what we can now do is, again, we can duplicate this class and say, okay, this is with direct electric heating, and move this up a little bit in the package view. And this one is without direct electric heating. And now again, what we have to do is we have to remove the identifiers in the base class. So to make it even clearer, let's rename this one to just partial building energy system. Partial means in Modelica language, it's an abstract class. And now we can remove the identifier of the transfer system and the control system in here. And now in the model with direct electric heating, you can select direct electric heating and self-consumption increase control. And in the model without direct electric heating, we just select no transfer, no control. And now we are able to simulate both. The one with direct electric heating is equal to the one I already simulated. So we can keep this one in the view. And now compared to the result without direct electric heating, I expect the results to not change drastically, because we almost always achieve room temperature. But still, we may see some slight nuances. What you definitely can notice is that due to all the shattering and bad control behavior and switching, simulation with direct electric heating is much slower. But again, we would have to optimize the control anyway. Now we can compare the results, and first looking at the room temperature, we can see as expected, there are not that many differences. And also at the grid level, I will quickly plot the electricity we generate we can definitely see that in sometimes we only for a short period use the electricity, and for other periods we don't use it and feed it into the grid. But I guess the best part shows it in here. We can clearly see how the results from, now I have to check again, not that I confuse myself. So this red line is with direct electric heating, and the blue line is the one without direct electric heating. And we can see a slight increase in room temperature. We can now also check, okay, why is the room temperature even falling in this case? The weather data is in both cases the same. And let's rescale everything. And we can see that it actually happens after a period of warm weather. And that could be due to the case that the elevation of the heating curve used to control the boiler is not set properly for the building model. So you could optimize this a little bit, but still the deviation to 20 degrees Celsius is not that big. So in here we only see a slight improvement. But what we could, for example, do in a study is we are not actually shifting any energy. So we are only controlling the direct electric heating to achieve the room temperature the boiler wants to achieve anyway. So what we could do is, for example, increase the set value and say, okay, if we have surcharge of PV, we can increase the room temperature to 22 degrees Celsius or something, and use the building mass for inertia and demand side management. Also, we definitely would have to increase or improve the hysteresis of the model, but this again does not show how direct electric heating could be beneficial or not. It just shows you how to add a module to BESMod. And finishing this tutorial, if you started working in a separate package like this one, you can just go, as explained at the start, to BESMod, open an issue, open a branch, and then, for example, I can just say cut this direct electric heating model, add it under systems, electrical, transfer, and then I will paste it in here. And the same goes for this example on or the test case for direct electric heating. So I can also put it in here. And for the control we created, I mean, the control is still pretty bad, so I'm not going to edit now. And also these models are fairly simple, so and have typos in them, as you can see here. They don't have documentation yet, so we would have to update this as well. But it's pretty simple to add models, and then you can just push them, open a pull request, and then we are happy to give you feedback and see if it is a nice addition to BESMod. So that would be all for the tutorial on how to add a module, and actually also on BESMod itself. I will add tutorials in the future, especially on parameterization, on how this works, but this is for another day. And I hope that the 5 videos given to you now enable you to use BESMod and be a better researcher by using coupled or domain-coupled building energy system simulations. So thanks, and if you have any questions, just write them in the comments or contact us on GitHub or via email. Thanks and goodbye.